Welcome to qnawire.
During the jump, the only force on the skater is airborne. The only force on the skater is gravity. She is airborne. So she's airborne. She's essentially a projectile in free fall, and so there's not going to be any force on the skater except for gravity, and this is acting through the center of mass. So essentially, we can there is no torque about the center of mass. And so we can say that angular momentum is conserved during the jump. For part B, we know that for a single axle, the skater must have 1.5 total revolutions. We know that the revolutions during each phase of the motion is the rotational frequency times the elapsed time. And so we can say that we also note that the rate of rotation is the same for both occurrences of the open position. So creating the relationship, we have 1.2 revolutions per second multiplied by 0.10 seconds plus the frequency multiplied by 0.50 plus, again, 1.2 revolutions per second multiplied by, again, 0.10 seconds. And we know that this must equal 1.5 revolutions. And so we can say that the frequency must equal 1.5 revolutions minus 2 times 1.2 revolutions, 0.10 seconds, and then divided by 0.50 seconds. And so this is equaling approximately 2.5 revolutions per second. This would be the frequency essentially for a single axle. And so the calculation would be the exact same for a triple axle. So continuing part B, we have 1.2 revolutions per second multiplied by 0.10 seconds plus frequency triple axle times 0.50 seconds plus 1.2 revolutions per second multiplied by, again, 0.10 seconds. And this must now equal 3.5 revolutions because this is a triple axle. And so we find that the frequency would be equaling 3.5 revolutions minus 2 times 1.2 revolutions per second multiplied by 0.10 seconds. And then this would be divided by 0.50 seconds. This is giving us approximately 6.5 revolutions per second. This would be our second final answer for part B. And then for part C, we're simply going to apply the angular momentum, the conservation of angular momentum, to relate the moments of inertia. And so for part C, we have moment of inertia of the single open equals moment of inertia of the single closed. And this would give us the moment of inertia of the single open multiplied by the angular velocity of the single open equals moment of inertia single closed angular velocity single closed. And so we find that the moment of inertia of the single closed divided by the moment of inertia for the single open, this would be omega sub SO divided by omega sub SC. This is equaling F sub SO divided by F sub SC. And this is equaling 1.2 revolutions per second divided by 1.52 revolutions per second. We'll round at the very end. This is equaling 0.476, and we can essentially round to approximately 1/2. So this would be the ratio of the moment of inertia of the single closed versus the single open. This is essentially meaning that the single moment of inertia must be reduced by a factor of 2. In order to do the triple axle calculation, it's the exact same thing. So we could say for part C, moment of inertia for the triple axle closed position divided by the triple axle open position. This would be equal to F sub TO divided by F sub TC. And this is equaling 1.2 revolutions per second divided by 6.52 revolutions per second. This is giving us 0.184, or we can say approximately 1/5. Essentially, the triple axle moment of inertia must be reduced by a factor of about 5 in order to make the triple axle. So this would be your second final answer for part C, and this would be your first answer for part C. That is the end of the solution. Thank you for watching.